And then can you mute everyone as well?
Except for me, right?
Yes. And then, yeah. You can unmute yourself, Linda, too, as well. It's just easier to mute everyone to start off with.
Oh, how do I do this now? I should have read the notes that I wrote for myself. Audio settings? No, that's my own audio settings.
Yep. Okay, I'm going to start. Hi, welcome to our July lecture. I'm Jessica. I'm the president of the SFAA. Just a couple quick notes before Linda introduces the speaker. Our members only Mount Tam star parties started back up again last month, and it was a wonderful event. We had the inversion layer happening, so it's 88 degrees at sunset. And we had the blanket of fog blocking out some of the light pollution from the bay. And our next star party is, this is weather permitting and state park permitting, is August 7th. If you are a member of the SFA and you do not have your parking pass for that event yet, the last day you can request it from the treasurer is July 27th. That way he has time to get it in the mail and the mail has time to get it to you before the event. So if you need, his email address is just treasurer@sfaa-astronomy.org. Just email him, or you can message me in the comments in the chat window and I'll give it to you. And then also, we are looking for images and stories about our club's history, about the SFA's history. Next year is our 70th anniversary, and we are getting ready to do some special things, but we would also like to collect as many images and stories about the SFAA and our past events and past members that we can. So if you'd be willing to share any images or stories, please message me and I will put you in touch with Douglas, who is doing a lot of our collection of the club's history. And again, I will put my email address in the chat window on the side. And then if you have any questions about the SFAA, again, feel free to message me either in the chat window here in the Zoom or just email me. And it's president@sfaa-astronomy.org. So over to you, Linda.
Oh, okay. I'm going to introduce the next 2 months upcoming speakers, and then I'll introduce tonight's speaker. We're having a special family-friendly presentation planned for Wednesday, August the 18th. It's going to be by NASA's Brian Day. The title is How Your Family Can Land on Mars and Explore the Solar System Using NASA's TREX. First, you're going to land on Mars's Jezero crater, where Perseverance is beginning its epic explorations. And then you'll journey across the surface of Mars and explore some other exciting locations. And then you're going to tour the moon and other worlds. You and your family will learn how to use NASA's TREX visualization portals and do your own explorations across the solar system. And you can 3D print any features that you'd like. I mean, how about having a 3D print of Olympus Mons? And you can do this at your home for free. And NASA will continue to expand places that you can visit as it expands its portal sites. And tell your family and friends to join us that night. I think it's going to be really terrific. And of course, it will be recorded and put on SFAA's archive, so you can go back and fine tune details that you might want to sort of go back and freshen your mind about. But it will be an amazing event by Brian Day. Then on April, this is always on the third Wednesday that we meet, on April 21st, third Wednesday, I mean, not April, let's see, here we go. On September 15th, Shooting the Stars, the Tales from the Stratosphere. Marita Beard is going to give us a talk about SOFIA. SOFIA is NASA's stratospheric observatory for infrared astronomy. And it offers teachers the opportunity to experience firsthand what it's like to be aboard the Boeing 747 with a 106-inch telescope flying into the stratosphere as an airborne astronomy ambassador. She will share her experience as a teacher, and she currently teaches AP Physics at Lee High School in San Jose. And San Jose Astronomy Association is where recommended that her talk would be very, very interesting. So two things that might be of interest to your entire family on next month and then September 15th. Tonight, Dr. Roger Blandford took his BA, MA, and PhD degrees at Cambridge University. Following his postdoctoral research at Cambridge, Princeton, and Berkeley, he took up a faculty position at Caltech in 1976, where he was appointed as the Richard Chase Tolman Professor of Theoretical Astrophysics in 1989. In 2003, he moved to Stanford University to become the first director of the Kavli Institute for Particle Astrophysics and Cosmology and the Luke Blossom Chair in the School of Humanities and Science. His research interests include black holes, astrophysics, cosmology, gravitational lensing, cosmic ray physics, and compact stars. He's a fellow of the Royal Society, the American Academy of Arts and Science, the American Physical Society, and a member of the National Academy of Sciences. In 2008 to 2010, he chaired a 2-year National Academy of Sciences decadal survey of astronomy and astrophysics. Dr. Blandford was awarded the 1998 Danny Heinemann Prize of the American Astronomical Society. In 2013, he received the gold medal of the Royal Astronomical Society. And in 2016, he received the Crayford Prize for Astronomy and the 2020 Shaw Prize for Astronomy. Tonight, Dr. Blandford will speak to us about fast radio bursts, astronomical puzzle, and cosmic probe. And we welcome Dr. Blandford giving us this talk and thank him so very much.
Hi.
So there you are.
Can you hear me?
I can.
Excellent. Okay, well, thank you very much, Linda, for your very kind introduction. I'm very happy to be here with you and members of the Astronomy Society. And I only wish, as I'm sure you did, that it was rather like the last time we talked when we were in person. And we all are eager to resume that sort of interaction. And at any rate, we'll do the best we can over Zoom. And as I've already said, if there are questions during this presentation, then I'm very happy to discuss them as they come up. It is probably better to work with the chat function. So I think just by way of introduction, I'm not sure how many people were here the last time I talked, but I did talk about neutron stars and in particular pulsars, and this talk is going to be a little bit in the same vein, but in fact it's going to be rather independent from it too, so there won't be a lot of commonality. And the topic we decided would probably be most interesting is this topic which I'm going to call fast radio bursts. And it's a very hot topic in astronomy at the moment. You're not going to see this from the top of Mount Tam with an optical telescope. Maybe you will, but as yet nobody has seen them with optical telescopes. It really is a radio astronomical phenomenon. But it's a very interesting one, and it's going off in a very interesting direction. And my hope in this talk is that I can communicate some of the excitement, some of the progress, and some of the prospects in the study of fast radio bursts. And I'll try and finish off by showing them how they're not just interesting in their own right, like so much of astronomy and astrophysics is, but they're actually useful as probes for doing explorations of the universe. And so that's one of the that's where I hope to end in this talk. It's a topic where we've learned quite a lot in the last few years, and as I'll try and communicate this, the prospects for learning even more are are very high for the coming years. And so I'm going to go out a little bit on a limb and tell you things that I think are going on. And I hope you'll forgive me if what we learn in the next few years shows how silly and wrong I was. But that's the nature of the business, and it's certainly one that's catching a lot of attention right now. So what I'm going to do, I think, is to try and I've got a few slides, not too many, and I'm going to try and share my screen, and we'll see how that works. So share screen, desktop to share.
Looking good.
And now I'm going to go to, here we go, slideshow, presenter view, and sorry, it started again the wrong place, but there we go. So you should see a title slide.
Yes, we do.
Okay, excellent. Thank you very much indeed, and thanks for all the assistance in getting this straight. Okay, so my title is Fast Radio Bursts, an Astronomical Puzzle, and we hope a cosmic probe. So let me start by showing you a few radio telescopes. I suspect everyone, they've probably seen the one on the top left-hand corner because it's been in the news a lot for a very sad reason. It's the Arecibo Observatory in Puerto Rico, which was a splendid radio dish that did sterling work for a very long time, but very sadly it had a catastrophic collapse and will observe no more. But it is part of this story, and it is and it has made discoveries about fast radio bursts. The one in the middle is the Parkes telescope in Australia, and this, as well as being famous amongst astronomers, there was a big movie made about it several years ago, I think, called The Dish, and it's rather a nice movie, and told the story of the moon landing and so on from through the eyes of radio astronomy. And it, in fact, data from the Parkes telescope was where the first fast radio burst was found. And then the one on the bottom right-hand corner is called CHIME. It is a Canadian telescope. And this was actually constructed for doing quite different types of science. It was basically done for doing almost conventional, but very ambitious observations of distant galaxies to learn about cosmology. And as happens so often in astronomy, and I'm sure you must have seen so many examples of this, you build a telescope to do one thing, and what it actually ends up doing is quite different. Now, CHIME will do its original job, and it's going along with that, but it's turned out that the very same telescope, and you see it's a very different type of telescope from the one from Parkes, for example, which is steerable. It's more like Arecibo, which of course is not properly steerable. But what it does is it allows the sky to transit over these sort of metal pig troughs, if you like, with lots of receivers along the line, along the focus. And it just records the data and just follows the sky as it goes over this telescope. And then with an awful lot of computing, you're able to deconstruct what it was you were looking at. And the original purpose was to look at essentially an assemblage of distant galaxies. But it's also been tremendously good for looking at radio transients, little radio flashes, and these include the famous radio pulsars, but they also include the fast radio bursts. And it's turning out to be essentially the prime instrument for looking at these fast radio bursts. And I'd like to show pictures of my friends who works, and this is Vicky Caspi, who's had a leadership role in getting this telescope going, and in particular in doing all of the electronics and computing that is necessary to use it for pulsars and fast radio bursts. And as I say, I think it's probably the most productive facility right now, but before long, there are many other telescopes that are being used primarily for this purpose. And here's one very ambitious one called DSA 2000, and that some of you may recognize. This is an artist's impression of what 2000 dishes are going to look like. And it's in the Owens Valley. I think there's about 100 or so of these so far, and I'm not sure whether they have the resources to do all of these. But one of the messages you might get from this is that the actual telescopes themselves are not very elaborate, not very expensive. Where you put all the effort and all the resources is in what you do with the signals from these telescopes, all of the electronics and computing and so on. And that's the bit that's state of the art. And people are learning an awful lot about signal processing, which is more generally applicable from studying these fast radio bursts. So I keep on saying fast radio bursts, but I haven't said what they are. So let me try and rectify that. They are very bright radio flashes. So they're seen with radio telescopes with some qualification, which I'll come to later in this talk. They are seen basically at relatively low radio frequencies. So they're seen at relatively low radio frequencies. Now, if we take the incidence of observed bursts, then they, and we sort of multiply by, if you like, the whole area of the sky, then they're probably happening about once every minute across the whole sky. So if you had radio telescopes looking at the whole sky all the time, then you'd probably see them about once every minute. It obviously depends how sensitive you are and everything else, but that gives you some idea that these aren't very rare things. They're happening all the time. Now, the first thing that was first one of these radio bursts or radio flashes that were seen was found using the Parkes telescope, which I just showed you, and it was found by a scientist in West Virginia called Duncan Lorimer and his student Narkovich, and they basically looked through old data from the Parkes telescope, and they found, this is actually the flash that they found. I don't know whether you can see my arrow. If you can you see my arrow? Is that working?
Yes, we can.
Okay, fantastic. So this was just the flash that they saw, and it was an event that happened, in fact, in 2001, and they were looking at the old data in 2007. So that's when they made the discovery. They didn't quite know what to make of it, and these were rather controversial for a while. And we'll come on to that in a moment, but this is a bona fide fast radio burst, and it was pretty clear from early on that they were intrinsically flashes that were very short. They were lasting like milliseconds. A millisecond is 1,000th of a second. So these are real flashes, and the sources of these, most of them were cosmological. That is to say, they're on the other side of the universe. So not quite sure what the most distant one we know about so far, but they're an appreciable fraction of the size of the universe. There were several other properties of them. I'll just mention a couple here. One is that these are radio pulses, but they are what we call highly polarized. And I suspect most of you know what polarized radiation is. If you have polarized sunglasses, the electric field in the electromagnetic wave swings from side to side. And it has two ways of doing it. It can go from left to right or up and down, if you like. And if you just see it going from left to right and not up and down, then it's highly polarized. And the same business can happen at radio wavelengths. And these pulses were found very commonly to be highly polarized. Now, an obvious thing that an astronomer, any of us would say is, well, do you get the same thing from the same source more than once, or is it a one-off thing? Is it like a supernova explosion? You don't get a star becoming a supernova and saying, well, that didn't work too well, I'm going to try it again. It's a supernova, it's the end of its evolution, if you like, and it has this giant explosion. That's it. So is that true of these fast radio bursts? And the answer turned out to be many of them have been found now to repeat. So it's a recurrent phenomenon for many of them. But we don't know if that's true for all of them. This is one of the big unanswered questions. But it's not impossible that essentially all of them will turn out to repeat. Again, I'll come back to that in a little bit. And then the other sort of typical question that astronomers will ask almost reflexively is, well, is there a periodicity there? Is there, if you look at a star and then you can see, is there a binary period in that star, which means it's got a companion that it's orbiting and so on. So are there periodicities here? And periodicities have been found. The most famous one is in one of these sources that's got a period of 16 days, which does look like it's a binary star. Now, I'd like to say a couple of other things, which I'll actually return to. If we look at these fast radio bursts with radio telescopes and look at them at different radio frequencies, it's like tuning your old-fashioned radio from one radio station to the next. We look at different frequencies. Then we find, as is exhibited actually in this graphic, and here we've got my arrow on, that the bursts, when you observe them at high frequencies, they arrive a little bit earlier than those that come at low frequencies. And this is something that radio astronomers are extremely familiar with. It's called dispersion, and basically what happens is that although we say light travels at the speed of light, radio waves in particular travel a little bit slower than the speed of light, and the lower the frequency, the slower they go. It's not a big effect, but it's big enough to give a small delay when you're crossing the universe. And the amount of that delay, which you can measure rather accurately and remove, the amount of that delay is going to increase as the amount of plasma, of gas, along the line of sight is increased. So we know the universe has got lots of hydrogen and lots of electrons associated with that hydrogen, just like our ionosphere has lots of electrons which affect the propagation of radio waves, as you know. The universe has these effects as well. And by seeing what the delay is, we can figure out how much gas there is there. So these are their intrinsic bursts are about milliseconds. And this was what Duncan Lorimer and his student discovered in 2007. And we've been learning about them ever since. And this, if you make an audio representation of this delay, we call it a sad trombone. Now, astronomers got involved in trying to explain this. They were taken seriously, and there were lots and lots of explanations. The first was that it was radio interference. Of course, this happens all the time on the Earth. There's a lot of radio interference. And then it turned out that some of these bursts were repeating. And they were not keeping sidereal time, not keeping the time of the stars, but they were keeping local time. And the time that they were keeping was round about lunchtime. And with a lot of careful scientific analysis, they figured out that some of these bursts were associated with opening the door on a microwave oven. And you have to believe me that there is almost nothing more embarrassing to a radio astronomer than to have this happen on their observatory. But nonetheless, these things were identified as just being seen not across the other side of the universe, but the other side of the observatory. And they were called peritons after H.P. Lovecraft, who created these mythical beasts seen here. Of course, they weren't all like that. The ones that we know, they were weeded out, and the ones that are real are really seen from across the universe. But still, they cried out for explanations, and my colleagues, in their imagination, if not sense, produced a huge panoply of explanations, and all of these are out there somewhere. I've made a list of them. In fact, there's lists on the web. I'm responsible for I'm only involved with one of these, I have to say, but aliens and cosmic strings and white holes. You've got black holes, why not have white holes? And entangled molecules. It all sounds like it's all made up, and it almost is. Quark nuggets, ball lightning. That's actually a real thing, but not connected with this. And then a bit more sensibly, active galaxies, something to do with supernovae. But as I said, the fact that the ones that repeat can't be supernovae because supernovae don't get a second chance. Merging neutron stars or black holes, they don't get a second chance either. And then we're becoming more sensible now. They could well be, many of these are pulsars. They're like things that are seen from the radio emission from pulsars, pulsating neutron stars, and then finally, and this is the one that I from day one have believed was what was going on, and I'm going to try and persuade you that this is what is going on, at least for a large fraction of these objects, is something that's related to a pulsar, but it's called a magnetar. And I'll explain what I'm talking about in a couple of slides. So these are the explanations. And I suppose if you want to take a very democratic view of this, you could say every one of these crazy explanations is correct for one fast radio burst. But I think most of us thinking scientifically would say, no, there's probably one or maybe two or three explanations for the whole set of phenomena there. And I'm going to try and persuade you that probably most of them are in fact magnetars. But if you have a very democratic view of science, then you can take that bottom precept. Okay, before I want to give us just two slides of context here before I get on to the fast radio burst, because they are relevant to my story. The first, and I suspect most people in the audience have heard of this, I want to say a few words about what are called gamma ray bursts. Now, these are bursts that have many sort of superficial similarities to the radio burst, but they're seen in gamma rays. They were first detected in the 1960s by satellites that were actually looking for nuclear tests and worse, and looking for the sort of gamma rays that they might create. And what they ended up finding were these cosmic explosions that produce gamma rays. And there are three types, really, of these gamma ray bursts. So there's a bit of a message here for all of us, in that here we've got this phenomenon, we can call it gamma ray burst, but there's three very, very different types of physical phenomenon going on associated with it. Just as I'm sure you know, in supernova explosions, there are different mechanisms at work in different types of supernova explosions. So it isn't just one size fits all. Let's say it may be true for the fast radio bursts. We will see. So if I take the second of these are so-called the long gamma ray bursts. These typically last about 2 seconds or more. They are now known to be associated with a small fraction of supernova explosions associated with massive stars. And they're really, if you can think about them as being the birth cries of a black hole. They're probably, it's not absolutely sure this second part, but they're probably made by a newly formed black hole. And you've got this collapsing star around it. It makes a jet of emission, as you can see in this graphic here. It makes this jet of emission, and that's where the gamma rays come from. And we see those with our gamma ray telescopes. The third type of gamma ray burst is what's called a short gamma ray burst, and that we now know is associated almost certainly with neutron star mergers. There's some doubt still in this, but it's a good bet that they're mostly associated with neutron star mergers, the sort that have been measured and detected by gravitational wave observatories like LIGO. So I suspect you've heard about LIGO and the gravitational waves that it's detected. Well, some of those events are merging, coalescing neutron stars, and they can make short gamma ray bursts. The third type of gamma ray burst is called a soft gamma repeater, and these were identified with young magnetized neutron stars, highly magnetized neutron stars, and I'll come to that in a moment in 2 slides. And we call these magnetars. And what I'm going to try and explain is why we think that these magnetars not only make these so-called soft gamma repeaters, a special type of gamma ray burst, but they also make the fast radio bursts. So let me back up to the other contextual side I wanted to show you. And this is one I do recall showing in my last talk here, which was about regular neutron stars and pulsars. Now, neutron stars are, just to remind you, are stars which have about a solar mass or so, and they are so compressed, they're like a giant atomic nucleus, and they have a radius of about 10 kilometers. So that's pretty small, and it's a whole star that's squashed down to nuclear density, and it's about 10 kilometers in radius. And a typical one has a field in sort of units, I'm not quite sure, never quite sure what units to use, but 100 megateslas is the sort of modern unit, if you like. But a good way of thinking about this is 3 trillion times the magnetic field strength on the surface of the Earth. So if we ask the sort of surface on the Earth that you might use with your compass or a pigeon might use, 3 trillion times that is the magnetic field on the surface of a neutron star. And on the top right-hand corner here are Jocelyn Bell, as she then was, and Tony Hewish, who discovered these things in Cambridge. And for me, this is a special picture because I was an undergraduate, first-year undergraduate in Cambridge University at the time that they made this wonderful discovery, and it was a wonderful discovery. And here actually you can see the data and so on. And what they found, and we now know of several thousand of these pulsars, and they're carefully measured, is that you have spinning magnetized neutron stars, and they have spin periods that range from about 1.5 milliseconds. So a day on one of these neutron stars is 1.5 milliseconds. If you want to play that on the piano, it's about top E flat, going down to about 30 seconds. And you see them throughout all sorts of ways, radio waves, gamma rays, and so on from them. And they go tick, tick, tick. And they're great tools for physics, as I explained the last time we met. Now it's time to get on to the magnetars, giving that context. And the magnetars are, we think, about 1% or so, and we might dispute whether it's exactly 1%, but it's not so wildly different that probably, of new neutron stars which are made in supernova explosions. And about 1% of these, we think, we're not sure, but it's about that, are going to become what are called magnetars. Now, magnetars are the fundamental way in which they are different from the regular neutron stars that I just described is that their magnetic fields, instead of being about 100 megateslas or so, are about roughly 40 gigateslas. That means they're nearly 1,000 times greater than those that we see on regular neutron stars. They're really extraordinarily powerful magnetic fields. And this means, if you like, they're about 1,000 trillion times the Earth's magnetic field, 1,000 trillion times the Earth's magnetic field. Now, this is an extraordinary magnetic field. It's basically a new frontier for quantum mechanics, and it's to a regular physicist, let alone an astronomer, this is a pretty exciting business. And people are trying to do experiments of particle accelerators and so on to probe the physics of these enormously powerful magnetic fields. Now, one of the things about these magnetars is, unlike the pulsars, which can have spin periods or days, pulsar days, if you like, as short as 1.5 milliseconds, these are typically have days that are quite long, about 3 to 10 seconds. And the reason for this is quite simple, is with these strong magnetic fields, it turns out, they slow down very fast. So whatever they start off with, it isn't very long before they're spinning relatively slowly. The day is still 10 seconds, so it's not that slow, but it's just, they're spinning fairly slowly by neutron star standards. And what is special about these magnetars is that, unlike with the pulsars, where all of the power that we see is derived from the rotation of the neutron star rotates, and it loses energy as it slows down, and that energy is what makes it visible to radio astronomers and optical astronomers and X-ray astronomers and so on. So we see all of that emission because of the loss of spin energy or rotational energy. It's like a top that slows down in the case of regular neutron stars. But in the case of magnetars, they've already slowed down. There isn't much of that left. And it turns out that the source of the energy are these enormously powerful magnetic fields. So most of the energy that's responsible for what we see is magnetic field. Now, this was a story that was told firstly by two theorists, one of whom was one of my close colleagues and friends, Chris Thompson here, and then Rob Duncan, and they proposed this as a somewhat wild, extreme idea. I mean, making these enormous magnetic fields. They had reasons for postulating this, and it turns out they were exactly right. And another of my friends and colleagues, Chris Akuviliotu, was able to, with her colleagues, was able to demonstrate that, in fact, this hypothesis was correct. And we now know that this class of objects, the soft gamma repeaters, the magnetars, are neutron stars. So what we have then is a neutron star with enormously powerful magnetic fields sketched here. Here's some data showing one of them rotating. I'm just going to show this is what the X-rays look like. It rotates. And then this is a cartoon. This is actually, sorry, so I take this back. That's a cartoon. This is an image of the sun with a magnetic flare on the surface of the sun. And this magnetic flare is an analog of that is happening on these magnetic field lines on the surface of the magnetar. And that is responsible for these gamma ray bursts, but also the radio emission. Now, given all of those theories or explanations that I listed a couple of 3 or 4 slides back, what makes me and should make you believe that we're probably in most of these cases looking at magnetars? Well, here is one piece of evidence that came up last year. Was one of these known magnetars that was a soft gamma repeater also made a fast radio burst. Now, it wasn't a very strong fast radio burst. In fact, it was a quite very weak radio burst, but it showed that these powerful magnetic fields associated with the magnetars could make something that looked awfully like a fast radio burst. And this is somewhat exciting for me. And today I learned on the Astronomy archive, which is where new results are posted. This happened today, literally today. And if I'd given this talk yesterday, you wouldn't have seen this slide. That instrument called CHIME that I just told you about has seen sort of not terribly good periods in the radio emission from one of these fast radio bursts. And the timescales are many milliseconds. And so we're actually seeing evidence for, it may not be a terribly good period, there are not very many of them here, but in one of these bursts, if you look inside it, you see something that's got periods of milliseconds and so on. So it's like there's some big, either some rotation or much more likely, there's a wave associated with the emission. And most of the other explanations that are out there cannot produce anything this finer structure in the emission. And so this paper, which I've not understood properly yet, it says many things that I'm not sure I fully understand, but this paper is claiming that this is really strong, further strong evidence that the fast radio bursts are associated with these enormously magnetized neutron stars called Magnetars. And and here I would agree with them. Actually, they discuss lots of possibilities, but the one that I would take seriously, and we'll come to this, I think, in the next slide. The one that I would take seriously is that that what we're looking at here, the sort of precipitating event, if you like, is not an earthquake as we would have on the surface of the Earth, and we're rather sensitive to in California, but a starquake, an analogous thing happening on the surface of a neutron star. So these are three of the well-studied fast radio bursts. And these fast radio, but we have many more examples. Of course, there are about over 1,000 that have been sort of fairly well studied, but these are three that have been shown this sort of quasi-periodic behavior. And it's thought that this is really further good evidence that magnetars are responsible. So let's try and think a little bit more about what might be going on physically. And as you can probably imagine, there are a large number of papers out there, including the alien spacecraft. And I'm going to just tell you about the ones that I take perhaps a little bit more seriously. A sort of cute way, if you like, of thinking about this. What I suspect is going on is to take the sort of classical Greek or Aristotelian view of the elements, earth, air, fire, and water. And so the analog of an Earth phenomenon is that it's essentially, as I said, a starquake. A neutron star has a solid crust, and just like the Earth, it can have a quake, and that quake can shake the magnetic fields around, and the magnetic fields will carry waves out away from the neutron star. So here we've got a quake here, and you can just a photograph of the sort of damage that you can get. Of course, it's scaled up much bigger on a neutron star. And then here is a metaphor almost for a magnetic wave. A magnetic field behaves a little bit like Indiana Jones's bullwhip here. And in particular, the bullwhip is rather wide near to his hand. And it has a very narrow tip at the end. And although the actual physics of this is a little bit more complicated than this, if you think about it simplistically, that tip moves supersonically. It creates a little shock wave right at the end, and that gives you the crack that you hear from a bullwhip, and that's an analog of that, but with magnetic field lines rather than the bullwhip, is what many of us think is responsible for creating this emission. Now, if you've got this magnetic field and you're moving it around at close to the speed of light, you're going to make a lot of electric field. This is what magnetic fields do when you move them around at the speed of light. They make electric field. And not surprisingly, this is going to give you a lot of lightning. This is the fire, if you like, in this description. So this is a part of the explanation. And then finally, as the sort of fourth metaphor, if you like, here, is a tsunami. And basically, as I'm sure everyone knows, a rather small, in terms of height, disturbance in the middle of the ocean can propagate across the ocean to strike land, and it can be focused or defocused. And if it finds a place that is set up for this, then it will make an enormously large amplitude wave, as you can see here, a tsunami. And the contention that I think others would have is that these fast radio bursts are essentially electromagnetic. That means electric fields and magnetic fields acting in this magnetosphere and behaving in much the same way as water does, making a tsunami. Now, I'm not going, unless there's questions on this, I'm not going to go into this in any more detail, but that's, if you like, the metaphor for what might be going on to make these fast radio bursts that are seen so commonly across the universe. So let me finish up where I said I would, and that is to say, well, these are fascinating objects. As astronomers and astrophysicists and physicists and the public and so on were always and should be always curious about how things work, what are the mechanisms that are actually responsible, and that I've tried to give you some hint of what I think the answer is, and maybe if I were giving this talk in 2 years' time, I'll tell you I'll deny that I ever said what I'm saying today and tell you something else. Maybe it is alien spacecraft, but I don't really think so. But independent of what the explanation is, they are useful. I mean, the sun, we took a long while to figure out what was going on the sun, and we now understand it rather well. But it's useful. It allows us to see in the dark. It allows us what would otherwise be dark. It keeps us warm and so on. It's rather a good thing. The sun, it has use. Well, to a cosmologist, these fast radio bursts have use, because one of the things that cosmologists are trying to do is to understand in detail the contents of the universe. And the major content is the gas. It's mostly hydrogen, and it's mostly hydrogen in which the protons and the electrons are separated, and that causes this delay shown graphically here. This is at the low frequency, and that's at the high frequency, and that causes this delay, which is a measure of the gas along the line of sight. There's also an effect, which I actually showed a graphic for, but I didn't make a big deal of it. There's not just this delay, there's also a scattering that happens, rather like the scattering that you're quite familiar with. It's rather similar to, actually, scattering you're quite familiar with when a star will twinkle in the sky, and that's due to scattering, and a somewhat analogous effect happens with radio waves. And that is an effect that actually is a measure of the gas in the universe. And then finally, this what happens to that polarized part of the electromagnetic wave, that also is a measure of the magnetic field along the line of sight. So these are splendid cosmological probes. This is an optical image made with Hubble Space Telescope of a gravitational lens. And for we're going to see many of these fast radio bursts in the future that are going to have multiple images of the fast radio burst. So if we miss it 1 month, we can come back a month later and find it's another image. And by getting these different lines of sight, we're going to learn an awful lot about the matter along the line of sight. And we can already see, whoops, sorry, I think, okay, so that one can seem to, so let's just go back to the slideshow. I'll do that one. Play from current slide, sorry. Yeah, there we go. Great. So we already know from a few of the early fast radio bursts, it's actually better than this now, that the further away the fast radio burst is, the more of this delay or dispersion that you see. And so this is pretty crude so far, but imagine repeating this exercise in many different ways with millions of these sources. And some people have said there can be billions of these things, but I think it's quite credible that there will be millions of them that observed in different ways. And then you'll start doing really rather precise investigations of cosmology. And that's a very exciting prospect, I hope, for the cosmologists, independent of understanding what the mechanisms that are at work in the fast radio bursts. And so with that thought, I'll stop here and ask for questions. Oh, I should probably, I'll stop share. There we go.
Thank you very much. We did receive one question in the chat from Tom Kellogg. Tom asked, what physical conditions create radio waves? Why do objects create waves in two extremes of MW radiation, gamma, and radio?
So MW?
Probably microwave.
Microwave, I've got it. Yes, excellent, yeah. Yes.
So what physical conditions create radio waves? And why do objects create waves in two extremes of microwave radiation, gamma, and radio?
Okay, an excellent question. Thank you very much, Tom. Let's go back to Arecibo, if I can. I think I'll just talk. I won't show the slide again. If we go back to Arecibo, it wasn't only a receiver. It wasn't just looking at the signals. It was also transmitting them. And one of the ways you transmit radio waves is that you have an antenna, which you have electrical current flowing along a wire or a metal rod or something like that. And that electrical current goes backwards and forwards, backwards and forwards, backwards and forwards. And that creates electric and magnetic fields. We call these electromagnetic waves, which are used, which are observed far away from the source, from the Arecibo. If you're looking far away from Arecibo, you would just see these electric and magnetic fields oscillating from side to side, and an electric and the magnetic field oscillating from side to side. In the case of Arecibo, you would say was a radio wave, or if you like, an MW or microwave. That's what you would say in the case of Arecibo. Now, if you speed up the action, then and you make the frequency of the electric field swinging from side to side faster and faster, then you'll get an infrared wave. And if you go faster and faster still, then you'll get an optical wave, and then an ultraviolet wave, then an X-ray, and then a gamma ray. And by the time you're talking about optical, ultraviolet, X-rays, and gamma rays, physicists tend to think about these not quite so much in the same ways they think about radio waves. They think about them more as what we call particles of light or photons. So they tend to think about them as particles. And somewhere in the middle, in the optical, say, we think about them as being both waves and both particles. And this is one of the things that the physicists do, is sometimes we talk about these electromagnetic waves as being sort of just waves in the way I first described it, or sometimes we think about them as particles in the way I second described it, which we call photons. And they're equivalent, and sometimes one is more useful, and sometimes the other is more useful. Now, in the case of the fast radio bursts, what we've got is something that's analogous to a very, very, very intense radio transmitter. And instead of having electrical current move along those metal rods, we've got electrical current move along that rapidly changing magnetic field. And that's what gives us these radio waves that we observe with radio telescopes. Does that help?
Yeah,
It was,
thank you.
There he is. We have another question. This one from Jim. If you are a supernova, how do you decide whether you are going to be an ordinary neutron star or a gravity?
Or what was the second option?
Or a gravity star.
A gravity, a black hole perhaps. That is a very interesting question, and one that astronomers have puzzled over for a long time. The simple answer is that if you're more than, other things being equal, if you're more than about 8 solar masses, then you're going to make neutron stars or black holes. But a range of the more massive stars, or ones with special conditions, are going to give you a black hole in the end. The majority of these so-called core collapse supernovae give you neutron stars in the end. That we do know. There's 1 billion neutron stars in our galaxy, or probably almost 1 billion neutron stars in our galaxy. And most of the core collapse supernovae, which you can see with optical telescopes, most of those are going to produce neutron stars. Now, some of the types of supernova, type 1As and so on, leave nothing whatsoever behind, like the Cheshire Cat. But most of them leave neutron stars. And a minority of the heavy stars that live fast and die young, the heavy stars, a minority of them will give you black holes. But delineating the conditions under which that happens is something that we have some understanding of, but I think it's not as secure as the other statements I have made.
All right, we have a new question here from Philippe. And feel free to ask by voice too. What is the typical time for which a magnetar decays into a regular neutron star?
Again, these are really good questions. You're putting your finger on the thing on all the right questions. And I wish I had better answers for you. We do have quite a lot of observational evidence. The magnetars that we know about, leave the fast radio bursts out of the story for the moment. The magnetars that we know about tend to be pretty close to the galactic plane and near regions of star formation, and that means that they aren't magnetars for very long. Perhaps hundreds or thousands of years, maybe 10,000 years, but not as long as a neutron star keeps its magnetic field, which is typically like between 1 and 10 million years. So neutron stars are believed to lose their magnetic field too, but on a timescale of millions of years maybe, whereas the magnetars use these colossal, stronger magnetic fields in maybe 100 years, just to take a round number. If this association of the FRBs with magnetars turns out to be right, then I think we're going to get a much better answer to that very good question. We're going to have a much more of a basis for answering it. But that's, what I've said is what, is I think is what most of us believe is the lifetime of these magnetars. So there really are young neutron stars that you're looking at.
Excellent. I see a hand up from Terrence. Go ahead.
Yes, can you hear me?
Yes.
I can.
Great. I'm describing fast radio bursts as being 1% of the neutron stars. That I got, but you listed 4 speculations on what actually might be going on causing the fast radio bursts inside the neutron star, and the analogies were star quakes, magnetic wave variations, lightning, and electromagnetic tsunamis. I was wondering if you could, all of which, in the analogous form at least, have a understandable cause. In an earthquake, something slips in the crust, some force that's built up over time slips. What is slipping in the 4 explanations of what might be causing the fast radio bursts in each of those cases? The magnetic waves, what is causing that to suddenly trigger, and where it doesn't trigger regularly? And lightning, that's a charge builds up in the atmosphere and is released unexpectedly. Electromagnetic wave tsunamis, tsunamis are usually earthquakes that generate those underwater. So if you could speculate a little further into the exact mechanism there.
Let me just clarify one thing. What I was describing with those 4 metaphors were not 4 different explanations, but one explanation in which that was features of what, all of those were features of what I would suspect are going on. Now, if we say what's the first cause, going back to philosophy, and then I think those of us who've embraced the magnetar idea for some time are really, perhaps, if you like, in 2 camps. One of them is to say the first cause is a solar flare. We've got a neutron star, which is, for these purposes, just a dumb immovable rock, and it's got magnetic field attached to it. But changes in that magnetic field, just like changes in the solar magnetic field, cause the magnetic field lines to get twisted and stressed until they reach a point when they snap, when they just find a new configuration as fast as they can. And you could, I'm not sure whether this is going to work, but if I take one of my cables here like this, I mean, this is again another not a terribly good metaphor, but if I twist this little bit of flex, sometimes it'll just do something like that. That's a sudden change in the lowest energy state, which releases energy. So that's like a solar flare, which is just, if you like, moving and twisting the foot points of the magnetic field on the surface of the sun, and then all of a sudden snap, and there's a solar flare, a coronal mass transient, as they call them, and that sends huge bursts of charged particles out to Earth and interferes with radio communication and endangers astronauts and all of that.
So if I could summarize a random variations like we might see in the weather or in underground in earthquakes and stuff, random unexpected variations that you can't really measure or pin down because they're so random.
Well, you can't, but I mean, we do know a lot, for example, about the solar flares. We know that there are correlations with the 11-year solar cycle and so on. Mm-hmm. And we do have a certain amount of understanding of how they are made. But that's the one possibility. I say there are two schools, if you like. One possibility is that it's really essentially a magnetic phenomenon going on above the surface. The other is that it's a star quake. It really is a change in the mechanical structure of the star, perhaps triggered by thermal changes or slowing down or something like that, that gives you a quake, just like we can have a quake due to changes in the Earth's crust. That will cause a quake, which may happen with the San Andreas in California and so on. And that then, the first cause is then something going on in the solid crust. And that is then reflected in shaking the magnetic field around on the surface. But the actual first cause is what's happening in the crust, not what's happening in the magnetic field above the surface. And I'll share with you this thought, which is that I sort of belong to the first school until I saw that paper this morning showing these quasi-periodic oscillations, and give me time to think it through. But if I'm looking for the most appealing explanation of what they're seeing, it's a mode of oscillation of the neutron star. I don't know that. I haven't thought it through. I haven't even read the paper properly yet. But if I were just, shooting from the hip, I would say it looks like a mode of oscillation in the neutron star, in which case I joined school too. But we'll see. I mean, there's going to be more discussion, a lot more discussion of this. And in particular, sort of people poring over the data and saying, do they really believe there's a period there, and so on. So it's exciting. It's exciting, all of this.
Yes, excellent explanation. Thank you for that. And we'll look forward to your coming back and telling us which was right.
Right. Yeah. Well, thank you for your excellent question.
Oh, I see a hand from Jim. Go ahead.
Okay, hi.
Hi, Jim.
Howdy. Good. Excellent lecture. Just thoroughly engaged in it. And I posed my original question very poorly, as it turns out. And I want to correct that and ask it again. And it basically was, if you have a supernova, presumably of some particular class that is appropriate, what may determine, and this is probably all going to be highly theoretical, whether on a 99% basis, the result is a regular ordinary pulsar, or on a 1% basis, that it is going to become a magnetar.
Again, a really good question. My colleagues have been exercised about it for some time. There is no good explanation. I can tell you some of the things that have been discussed, and they're all plausible. There's lots of stuff that's plausible here, but figuring out what's important is not what we're trying to do, but we've not got there yet. So the sort of things which are plausible are, if you consider these stars themselves before they become supernovae, the final stages of their evolution are really rather complicated and probably rather idiosyncratic. Things like, people were shocked when they discovered what had happened in the supernova in 1987. I think you're maybe just young enough to remember the supernova in 1987. I'll admit to being that. And yet, it became clear that something very strange was happening before it underwent a supernova explosion. And it's things like, well, did it have a binary companion? What was its composition? How did it lose mass? The losing of mass is terribly important. It depends a lot on the composition. And if you've got lots of metals there, you use a lot more mass than if you don't have lots of metals there. What's the distribution of rotation? That again can be a very subtle business. Stars slow down as they age. They don't spin as fast. But how big an effect that is may depend on magnetic fields in the middle of the star, which may depend on a lot of sort of thermal history and so on. There's no sort of simple pathway. There could be a lot of idiosyncratic things that are going on. And so my guess is that the two ingredients out of all of those I've suggested that are most important are the amount of magnetic field that actually is there in the middle of the star before it collapses, and the amount of rotation. Those are my guesses. Those are the two factors which determine whether or not it gives you a magnetar, which is a rather special thing, or whether, like most of the collapses, again, we're not totally sure about that, but I'm going to guess that it's most of the collapses just give you regular neutron stars.
Thanks.
Thank you. Excellent question.
We have more questions on chat if you still have time.
I have time, so
right.
I don't want to keep anybody beyond their dinner or what. But I have time. I love talking about this. But you're in charge.
All right, very good. We have a question through Facebook. Stephen asks, "What are the nearest neutron stars and black holes to Earth?"
Nearest neutron stars and black holes. Well, the closest ones are we're not totally sure, obviously, but probably there's a neutron star. We may not be able to see it because it may no longer, it'll be an old one, no longer a pulsar or anything. It may be, 3 billion years old, but it's not unreasonable to have one that's, say, certainly within 100 light years. So that, and we may not be able to see it. It may just be old, tired, little magnetic field, little rotation, just sort of sitting there like a blob. And there's no particular reason for us to pick it out. The closest that we know about of these stars are about 3 times that distance, I would say. I think from where it's a little bit hard to get their distances, but the closest are about 3 times that distance. For the black holes, we don't know how many there are in the galaxy. We've seen, probably in binary stars, we've seen about 30 of them in our galaxy. But the expectation is that, people guess that in total there's about 1 million or so of them. We don't know that for sure, but that would be a sort of educated guess as to how many. And there are ways of finding them, not just when they're in binary stars. And one of them is the so-called microlensing. If you've got there's been obviously a lot of discussion of this. We have a star pass behind another star, then the gravitational lens effect, which I showed you an image of on a galactic scale, can happen within our galaxy using stars. And this is something that Einstein actually first thought about. And it's a rare phenomenon, but there are lots of stars out there, so it's actually observed quite commonly. Now, suppose that the thing that's doing the gravitational lensing is deflecting the light. There's nothing coming from it, but it's got a mass that's too big for a neutron star, then it could easily be a black hole. And that's one of the best ways of finding black holes in our galaxy, is to use this sort of microlensing to find a population of black holes that might that would give us a better handle on the number of those that are made in stellar evolution. But I guess it might, I think my educated guess would be 1 million black holes in our galaxy and 1 billion neutron stars. The black holes are heavier, of course.
Thank you. We have a question from Philippe. Given that a fast rotating neutron star to some extent contains its intense gravitational field, is there a scenario by which an aging neutron star whose spin rate decreases could eventually collapse into a black hole?
Oh, yes. Again, a very perceptive question. These are great questions. Yes. And some people say this may have happened in something like 1987A. If you have a rapidly spinning neutron star that's, say, got a mass of, say, 2.5, I'm just going to pick a number out, 2.5 solar masses. It's too heavy to be a neutron star slowly spinning. But if I spin it near its maximal speed, then it can avoid gravitational collapse to make a black hole. That's a real possibility, and people have thought seriously about that. Now, have this thing and let the magnetic fields do their work and do their job and slow it down. Then you may find that it can no longer resist gravitational collapse, and it will then, in a delayed way, make a black hole. And many scenarios for explaining supernova explosions have that as an option, as a feature. So yes, the answer is that can happen. And maybe it may even be that we'll see something with LIGO that will be a telltale sign of that.
We have a question from Owen. Would a particle orbiting in a spinning black hole's dragged frame near the speed of light emit something akin to Cherenkov radiation when it leaves, say, in a jet?
Well, Cherenkov radiation requires, I think I know where this question is rooted, and without going down a rabbit hole, I would say not in the way you might be thinking, I think would be my answer to that question. I see where this is coming from, but the Cherenkov emission, let me just say, is what happens when a charged particle travels slower than the speed of light in vacuum, but faster than the speed of light in the stuff in which it is moving. When it does that, it's a bit like a supersonic aircraft traveling faster than the speed of light. It makes a shock front and a sort of electromagnetic shock front. And when we stare at that shock front from afar, that's what we call Cherenkov radiation. And so the thought that probably underlies this question is that we're playing the same sort of games in the region around a black hole. But the problem with this for a particle is that locally, in general relativity, everything looks like it's just regular flat space-time, just like the space-time around you and I today. Locally, it's going to look like that. It's only globally that you get all this amazing and impressive curvature of space-time. That's only made manifest on the scale of the black hole, not on the scale of the particle. So that's why if I've not misunderstood the question, I would say probably not straight Cherenkov radiation, but are there effects that are analogous to this? The answer is yes, yes, yes. They sometimes go by the name of super radiant scattering and so on. And I think at the level of metaphor, you can say this has some of the flavor of Cherenkov radiation.
All right, thank you. Terrence, your hand is up.
Yes, it's been up since the last time. I think the moderator needs to take it down. I think that I can't do it.
Jim, your hand is up too. Is it?
If it is the same thing.
Okay, very good. Lowering your hand now.
Thank you.
We have a question in the chat from Philippe. When a neutron cools down sufficiently that it is no longer radiating thermal energy, is it a reasonable guess that its surface would have a metallic appearance?
Lovely, yes. Let me just back up a little bit. If I make a young neutron star in a supernova explosion, it will start off with colossal temperatures inside the star that are hundreds of millions of degrees, maybe up to 1 billion degrees or more, very early on. But the way this is actually organized is that the inside of the star is all pretty much at the same temperature. It's a very good thermal conductor, and so the temperature is pretty uniform all the way through the interior. Then we have this very thin blanket in the outer part of the neutron star, where the conduction by the different mechanisms is not so efficient, is not so good. And that's in some sense the thermal, but that's the blanket that keeps the heat in. Now the heat travels through that sort of spherical surface, if you like, and then appears on the surface of the neutron star, and it will have a much lower temperature than the one I just suggested. And there, that's what will be radiated, and ultraviolet and X-ray astronomers can actually see this hot surface of the neutron star. In the case of the temperature might be, in the example I gave, something like 10 million degrees, and in a neutron star like the one in the Crab Nebula, it would be about 6 million degrees. Now, the question says, well, what happens after a very long period of time? Well, the inside really does lose energy, and the way it loses it initially is through radiating neutrinos. So it creates a lot of neutrinos. They care about nothing. They're not stopped by nothing. They just leave the star and they take away energy from the inside the star. But eventually that becomes ineffectual. And so you're stuck with just regular heat transporting itself out to the surface of the star. But eventually the star itself will cool down. So if we think about an old neutron star that's stopped being a pulsar or stopped being any good to anybody, and it is, say, 3 billion years old, then it might have quite a low temperature. But it's probably not going to be an exactly solid surface. There's probably still, I think it's still the case that you have an atmosphere above what is, there is a solid surface, but there is an atmosphere above that. So we talk about the melting temperature of the crust of a neutron star. So one that's, say, 1 million years old will have a melting temperature that is the sort of, which happens at the interface between the solid crust and a fluid surface on top of it. And as the star cools down, that solid surface will go further and further out, but there will always be a fluid, essentially an atmosphere on the top of it, I think. So the extent to which it's the surface that you're looking through this atmosphere is metallic, people have thought quite a lot about that. And it is almost by definition a metal because it's a good conductor, but it isn't the same as a metal that you would have, an engineer or whatever would recognize on Earth. So it really has rather distinct and interesting properties. And one of the things, of course, that's terribly important is if it has any magnetic field left, even small amounts of magnetic field, that will have a big impact on the transport of the heat. So again, an interesting question, which we have only a partial understanding. There's analogous sets of questions which you can ask about white dwarfs, which when they're very old and what they look at. And there's actually been more activity in that area, and of course a lot of observations, and people's original thoughts have been modified partly by calculations but mostly by observations. So that is also a very active area, asking the analogous questions for white dwarfs.
Excellent, thank you. I'm not seeing any further questions, so Jessica or Linda, do you have any words for us?
Just how incredibly exciting and interesting, and I'm so glad that it's been recorded so I can go back and correct my notes that I've been scribbling all along. And no, it was wonderful, and we so appreciate your time and interest and your wonderful way of having it be so exciting. And I love the metaphors Metaphors were wonderful.
Well, thank you
I
very much.
appreciate it.
And-
Appreciate it very, very much.
And if anybody has a good idea for what's making those periodicities, please let me know. I'm still sort of taken aback by that, and I have to think a lot more about it. So it's it's nice when science happens in real time.
All right. Well, wonderful. Thank you
Thank you.
everyone for coming.
Thank you very much
you all.
indeed.
Thank
Thank
you.
you. Bravo.
Keep
Thank you,
well.
Dr.
Bye-bye.
Blandford.
Keep
Thank
well.
you.
Thank you.
Thank you.
Thank you very much.
Keep well and enjoy your trip to Mount Tam.
I
I hope somebody rides a bike up there.
Yeah.
used to do that, believe it or not, at least once a month.
Good, excellent.
Yeah, I used
applaud
to.
you.
Yeah.
I'm not going to be using any gas